All right, I'm going to talk about continuity with this video. So first thing we need to do is define continuity. We want our rigorous definition of continuity. So there are three pieces that must be true for a function to be continuous at a point. So this is at a specific value x equals c. So here are the three things. F of c is defined. So there must be a point there. You can't have an open circle, can't be an asymptote, or anything like that. Second, the limit as x approaches c of f of x exists. So the limit has to exist as well. You can't have the limit from the left and the right being two different values or something like that. All right, and then finally, the limit as x approaches c of f of x has to equal f of c. So that limit has to equal the value of the function. So the function actually has to approach that closed circle point on the graph. All right, so we're going to sketch a few graphs that break these rules. Okay, so rule number one, f of c is not defined. All right, so I'm going to just draw my xy axis for all of these. All right, so an example of f of c being not defined would be like if there's an open circle there. And then you have a function that may or may not go to that circle. All right, you could also have an asymptote instead. So I'm going to draw an asymptote in here. So that's a possibility as well. All right, part B, the limit does not exist. So one example of that could be the function approaches different values from the left and the right. Something like that. So f of c is defined. It has a closed circle, but the limit does not exist. All right, part C, f of c is defined. The limit does exist, but they don't equal each other. So that would be where like a function might go, didn't mark my C here. The function might approach an open circle like this. So that limit exists because it's approaching the same value from the left and the right, but then the closed circle value is somewhere else. All right, so the limit is not equal to the value of the function. All right, and then a continuous function would be where the function is approaching that closed circle value from the left and the right. All right, so there are three types of discontinuities. So if a function is not continuous at a point, x equals c, then it will fall into one of these three types. All right, a point discontinuity is where you have a hole. All right, so this is also called a hole. A jump discontinuity is where you have a limit that approaches different values from the left and the right. So it jumps. And an asymptotic discontinuity is where your function approaches an asymptote. Something like that. All right, a point discontinuity is said to be a removable discontinuity because a function can be redefined at a point in such a way to make the function continuous there. So you could take the original function and make it a piecewise equation, and just that second piece of the piecewise will fill in that hole and turn that hole into a closed circle, and now it would be a continuous function. Okay, so that's why it's called a removable discontinuity, because it's very easy to redefine the function. The other two, jump and asymptotic, are not removable, non-removable. And that's because you can't redefine the function. You would have to move this entire section of this graph up to match that, and that would be fundamentally changing the original equation. Same thing over here. You would have to somehow make these connect to each other, and you would be fundamentally changing the entire equation to do that. So you cannot do that. All right, so point discontinuity is the only one that is removable. All right, you can also be continuous at the endpoints. This is kind of a disputed fact a little bit, where when we're discussing continuity, and then later on when we discuss increasing, decreasing, concavity, is it increasing or decreasing? Is it continuous at the endpoint? All right, with continuity, we have a well-defined version here, where some of the other stuff math people don't agree, and so they don't have anything defined. But with continuity, we do. And the way you do that, because you can't do a limit from the left and the right because you're at an endpoint, you just do a one-sided limit. Okay, so the limit as x approaches a, so where a would be the left endpoint, where that limit is equal to the value of the function. And if you're at the right endpoint, you want to do the limit from the left of f of x. So I think this is best demonstrated with an example. So we saw this in our pre-cal review. Remember that this is a semicircle, radius of 5, center at 0. So I'm going to draw that out over here. I'm not going to do tick marks, just label that. Here's a 5 up here. All right, so we have a semicircle, looks like that. And it has endpoints there, closed circles. Okay, so we would say that this is continuous on -5 less than or equal to, so the -5 is included and the +5 is included for continuity. And that's because if you do the limit as x approaches -5 from the right, so we're coming from the right on this function, and we are approaching that closed circle right there. So it's equal to f of -5. They're both equal to 0. So that's continuous at the left endpoint. And then you do the same thing for the right endpoint. You approach from the left. X approaches 5 from the left. Oh, forgot my negative there. -5. No, sorry, that was correct. X approaches 5 from the left. So we're approaching 5 from the left, like that. And it's approaching a closed circle, which is f of 5. Those are both equal to 0. So it's continuous at the endpoints there. All right, so we're just going to look at a few functions here. We're going to identify the value where it is discontinuous. We're going to identify what type of discontinuity it is, point, jump, or asymptotic. We're going to identify whether it's removable or not removable. Remember, if it's removable, it'll be a point. That's the only one that's removable. If it is removable, we're going to redefine the function. So we're going to rewrite it as a piecewise function. So it will be continuous, and then we're going to sketch the graph at the end. All right, so anytime you're looking at a rational function, which is what a and b both are, if the denominator can be equal to 0, that's a discontinuity. Now, it could be, it depends on what type it is. It could be an asymptote, or it could be a hole, a point. So anytime you're dealing with rational functions, you almost always are going to want to factor what you can. So that's what we're going to do up here. We get x minus 3 times x plus 2. And then we have our x minus 3 on the bottom. So you can see how those x minus 3s are going to cancel out, leaving us with just x plus 2. And so when that happens, because the original function had a denominator, whatever that denominator is, so this is going to answer question number 1, find the values of x at which the function is discontinuous, that is a discontinuity automatically. Doesn't matter that it got canceled out later on. That's a discontinuity. Now, when it gets canceled out like this, it's not an asymptote. That's what you usually get when the denominator is equal to 0 as an asymptote. But if it cancels out like this, you get a hole. So this is a point discontinuity. All right, and then we know that point discontinuities are removable. So we are going to redefine our function, f of x equals piecewise. Okay, so it's going to be equal to this function, this exact function we started with, x squared minus x minus 6 divided by x minus 3. And that's going to be true everywhere where x is not equal to the discontinuity. So where x is not equal to 3. All right, and so the second piece is going to be where x is equal to 3. This is where we would need to redefine this function. All right, and the way you figure it out, it's always going to be a single number because you're redefining one point on the graph. That's it, that single point. Okay, possibly, I guess you could have multiple point discontinuities, so you may be redefining it at multiple points, but each spot is only going to be 1 point. So the way you figure out what that number is you take your 3 here, x equals 3, plug it into the reduced form. So 3 plus 2 would be 5. And that's it. So that's our redefined function that removes the discontinuity and makes a continuous function. So this piecewise function right here, this is a continuous piecewise function. All right, last thing is to sketch the graph. Pretty simple one. This is a linear function, x plus 2. I'm going to make sure to identify that hole at 3, 5. Right there, and that should be it. Okay, and if I were to graph this function down here, it would be this exact same graph, except I would put a closed circle there because I redefined at 3, it's equal to 5. And I'm going to leave it open, though, so we can see the discontinuity. All right, so part B, I'm going to have a lot of similarities with part A and then a couple of big differences. So number 1, exactly the same. It has a denominator. Wherever that denominator is equal to 0, that's a discontinuity. All right, but since we do our numerator is just a 1, it's not going to cancel out this time. So that means it's not a whole. Anytime the denominator is equal to 0 and it's not a whole, that means it's an asymptote. So this is asymptotic. All right, asymptotes are not removable, so this is non-removable. All right, and then we just need to graph it. So it's bottom heavy, so it has a horizontal asymptote at y equals 0. And then if I plug in 0 for x, I get negative a third. So that's a y-intercept right there. So this curve is going to go like this. And then there's no togetherness because it's not a perfect square. So the other curve has to go up here. All right, next. Okay, so this function, so it's not continuous for all real numbers, but where this function is defined, it's always continuous. Okay, so if I plug in 1, I get 0. So 1, 0. If I plug in 2, I get 1, 2, 1. And if I plug in 5, 3, 4, 5, 5 minus 1 is 4. Square root of 4 is 2. So this is what this function looks like. All right, and this function is continuous. Okay, now it's not defined for all real numbers, so it's not continuous over here, but we don't really worry about that with continuity. All right, continuity is always assumed to be on the interval where the function is defined, which this is defined from 1 to infinity, and it is continuous from 1 to infinity. So that's it for that one. All right, let's check this one. So piecewise functions are always a little tougher. I'm going to suggest we graph it first, and then we can come back and talk about continuity after. So I'm going to plug in 1. 1 plus 2 is 3. So there's 1, 1, 2, 3, and it's not equal to, so that's an open circle. And then we go left of 1, less than 1. So left, my slope is positive 1. So I'm going to go down and left like that. Down and left, down and left. All right, so like that. Okay, I'm plugging 1 down here. 2 minus 1 is 1. So 1, 1. That's also an open circle because it's not equal to. And then we're greater than 1, so we're going to the right, and the slope is negative 1. So I'm going to go down 1, right 1. Down 1, right 1. Like that. All right, so this definitely has a discontinuity. It's a jump. So the discontinuity happens at x equals 1. That's usually where it'll happen in a piecewise function. Think about these graphs just by themselves. That's linear. Linear functions are always continuous. This is also linear, always continuous. So the only possibility for this piecewise function to be not continuous is where they connect to each other, which would be at x equals 1. And so that's where our discontinuity happens. We can see visually from the graph that it is a jump discontinuity. Jump discontinuities are non-removable. All right, last one for this. Now we are given another piecewise function, kind of similar to our last one, but now we have this k, mysterious k in here, and we're asked to find k so that f will be continuous. So we want to make sure that this graph is continuous, and after we find k, we can sketch the graph over here. All right, so part A is that f of 2 must be defined. Okay, so f of x, f of 2. So we have equal to up here. So I plug in 2, and that's equal to 2 plus 3, which is 5. Okay, so first part of the definition of continuity is true, and it's equal to 5. Second part, the limit must exist. Well, for a limit to exist, it must equal the same thing coming from the left, coming from the right. So we're going to do a left-hand limit and a right-hand limit. The limit as x approaches 2 from the left. For coming from the left, we're doing the top function, x plus 3. And that's equal to 5. Just plug in the 2. And then we do the limit as x approaches 2 from the right. So from the right would be the bottom function. So that would be kx plus 6. And if I plug in 2, I get 2k plus 6. All right, well, for this limit to exist, these two have to equal each other. And we want it to be continuous, will be continuous. So set those equal to each other and solve. So 2k is equal to -1. So k is equal to -1/2. All right, and we can see that if I plug in -1/2 right here, I get -1 plus 6, which is equal to 5. Both of those are equal to the function, which means that the limit as x approaches 2 of f of x is equal to f of 2 when k equals -1/2. So f of x is continuous at x equals 2. All right, so I just need to graph it and we're done. All right, so the left side, plug in 2, I get 5. Closed circle. And then I'm going to go down and left. There's my y-intercept. Like that. All right, and then if this is -1/2, x plus 6, plug in 2, I get -1 plus 6, which is 5. Now, it would be an open circle, but this closed circle we already have there takes precedent. So it's going to stay a closed circle. And then I go -1/2, so I go down 1, right 2. Down 1, right 2. Down 1, right 2. Like that. There's our continuous function. Limit approaches the same value from the left and the right, and it's approaching a closed circle, which is what you need for continuity. All right, you have a good day. See you on the next one.